Well, it's pretty obvious. This one, I usually click don't allow here, but apparently there's a lot of people that click allow. And so as a result, there is an exponential growth in spatio-temporal data. So not only is there an exponential growth in spatio-temporal data, but there's also a lot of varied organizations that are collecting this data. So everybody has a mobile phone that doubles as a geolocating sensor, and every other mobile phone app asks for your current location and then records the location of your interactions with their web service. As a result, traditional multi-dimensional indexing techniques are straining to keep up. Techniques like R-trees that are embodied in databases like PostGIS. And I'm going to show you how PostGIS does not stack up to a particular data set that we worked with. So how do we address all of this growth in data, spatial data? There's two aspects to that. The first aspect is storage. In our case, we're leveraging distributed databases like Accumulo. And for those of you who don't know what Accumulo is, I'm going to describe it in a bit more detail in a moment. And the second aspect is obviously compute. We want to harness the power of Hadoop and other parallel computing frameworks to do spatial computations and to process spatial queries. GeoMesa sits as a foundation underneath of that. It's a spatio-temporal index on Accumulo, which I'm going to go into detail in a second. Right now. So GeoMesa is primarily a flexible spatio-temporal index built on Accumulo. It's flexible in the sense that you can scale it to the different resolutions of data that you may have. So for instance, if you have data that's worldwide, you can use a particular format of the schema, a particular configuration of the schema. If you have data that's only countrywide or statewide, you can have a different schema. And the same goes for the temporal dimensions. If you have hourly updates, you can configure the schema in such a way that's different than daily or weekly updates. Second, we've worked really hard to build an implementation of the relevant Geotools interfaces that expose this for integration in many different applications. I'm going to show you how simple it is to move from PostGIS to GeoMesa. Additionally, the Geotools interfaces are a very nice Java API, but if you don't have a Java API or you have existing OGC clients like OpenLayers or Google Earth or any of a myriad number of clients, you can access it through GeoServer plugins that we've built that expose the data that's in Accumulo, that's stored in GeoMesa, through standard protocols like WFS and WMS. So in terms of integration, here's a little bit of code. Hopefully you can read that. Top left is getting a handle on a data store object for PostGIS. Bottom right is getting a handle on a data store object for GeoMesa. As you can see, it's very little code change. I'm simplifying a little bit here, but if you have a geospatial application that's developed against Geotools, migrating to GeoMesa and gaining the advantages of a cloud store is very simple. So for those of you who don't know what Accumulo is a sorted distributed key value store. This is a quote from the Accumulo website. It's a robust, high-performance data storage and retrieval system. It's based on the Google Bigtable paper, which came out in 06-07. Google Bigtable has inspired many derivatives, including HBase, which is pretty much the biggest one, but then there's also Cassandra, and there's some other column family-oriented databases. So it is a column family-oriented database. Sorry, I wanted to go back there for a second. What Accumulo brings to the table that is enhancements over the general Bigtable paper is two particular features. One is cell-level security, so you can do fine-grained cell-level security for your spatial data, and spatial data is inherently personally identifying, so this is pretty important. Number two, we leverage to a large extent a server-side programming model that Accumulo provides that's not exactly provided by the other tools. So HBase has something called coprocessors, which is somewhat similar to this, but this is much more robust and mature than HBase's coprocessors. Basically, Accumulo, its extension point is these iterators. So you can think of these iterators as sort of the hooks that PostGIS exposes for spatial databases like PostGIS to exist. So what we've done is implemented iterators that provide spatio-temporal filtering semantics as the extension point for Accumulo. I already mentioned it's a column family-oriented database. The key is decomposed into a 5-tuple. Visibility is the security element of that. We take advantage of all of these different elements of the key, and the value is an uninterpreted blob of bytes. The Accumulo is a distributed database, so it's essentially a dictionary where it distributes data across tablets, and each tablet, so the first tablet that you see contains rows A through B. The second tablet contains rows, all the rows that begin with C. The third tablet is row F. So it's essentially a dictionary structure. It stores the bounds of a table. So it's a linear sort ordering of the keys. And that presents a challenge for spatial data because spatio-temporal data is multidimensional. So how do you represent multidimensional data in a sort-ordered dictionary? You use space-filling curves. So space-filling curves, in particular, we're using a z-order, or also known as a geohash. They have the property of projecting multiple dimensions down into a single dimension. And this gives us the ability to, using a base 32 encoding, to have a Accumulo-friendly, lexicographically ordered key. There's some other properties that we leverage to a large extent, such as recursive nesting. I can go into those in much more detail, but they might be a little boring in this context. So let's see. Now, this is sort of the heart of the matter. This is how we translate events, spatio-temporal events, into this index structure. So what you're looking at here is space-time events in San Francisco. And the first thing we have to do is we have to construct an Accumulo key. So we start with a random shard ID. The random shard ID is related to the number of tablets that you have, and the idea is that the random shard ID is represented here by a different color for each event. So you can think of each event as landing on a different tablet. And what this does is it uniformly disperses the data across all of the tablets in your cloud. So in this context, all of the data within this one spatial resolution will be spread across your cloud. And what this allows us to do is it enables us to leverage all of the compute resources and all of the storage resources to process various different types of queries. This gets around problems such as hotspotting, which I'm going to describe in a little bit more detail in a second. So that's the random shard ID. Second, we use the space-filling curves to encode the spatio-temporal dimensions of the data into an Accumulo key. This is represented here as these gridded boxes. The text in the boxes is a geohash. That's an URL-friendly encoding of a spatial location. It's actually a box, and we use that in terms of the recursive nesting of the space-filling curves to get advantages when we're doing our queries and scans. The effect of this is that if you look on the far right, those are a stylized version of the tablets, and what we're getting is a striping of the data across the cloud. So you can think of this almost like a RAID type of operation if you're thinking low-level file access. Finally, when you go to do a query, you construct this stack of iterators. This is the composable iterators that I mentioned earlier. And in our case, we not only do spatio-temporal filtering of the keys, but we do fine-grained CQL filtering of each candidate data point. So CQL is an OGC standard common query language for querying spatial data. We serialize the SQL, deserialize it server-side, and process each candidate result so you can have any kind of arbitrary attribute filtering or arbitrary polygon filtering, fine-grained time resolution filtering, et cetera. So this is a pretty busy slide. So a couple of the things that I want to get across. This is what the data looks like laid out in Accumulo. There's two takeaways here. One is at the top of the screen is the GeoMesa index model. What you can see is that we decompose different elements of the data into the row key, which is one portion of that 5-tuple, the column family, column qualifier, et cetera. what we're able to do here is put portions of the lowest resolution of the spatio-temporal data into the row key and finer resolutions into the column family. And we can leverage the sort order and tablet dispersal of Accumulo, as well as bloom filters, which they have on all of the column families if you enable it. And that gives us a fairly rapid filtering capability. Another thing to note here is that this is how we get the flexibility of the index. So we can specify that we want 20 bits of spatial resolution in the row key or 15 bits, depending on the resolution of your data set and the types of queries that you have. One other thing to note here, we are reusing we're using a variant of a pattern that is used in Accumulo. The pattern is the intersecting iterator pattern, and it's on their website as the indexing Wikipedia example. So we've broken each row into an index portion of the row and a data portion of the row. So we can search the index, and if we get a hit in the index, we can traverse the data portion. This reduces the amount of disk I/O that we have to do. OK, so how does GeoMesa perform? When we evaluated GeoMesa, the idea that we wanted to evaluate it in the context of moving from a traditional architecture to a cloud architecture. So we looked at the GDELT dataset. GDELT is the global database of events, language, and tone. It's out of a group at UT Dallas and UPenn. It consists of 220 million geocoded events from some unstructured text sources, many unstructured text sources, and it exhibits pathologies that are pretty common in spatio-temporal data sets. The first one is hotspotting, so you can see that this chart is showing on the x-axis the lexicographic geohashes across the entire world at 21 bits of resolution, and the density of events in the GDELT data set for each one of those geohashes, which again is a little rectangle. You can see that Washington has the highest number of events in its geohash. So this is hotspotting. If you were to store the data linearly, you would incur a lot of cost on a single CPU or a single disk. So we get around that by using this uniform dispersal technique. Another problem that is very common is that there are a lot of events at latitude 0, longitude 0, and that's because of bad geocoding. So if I were GDELT, I would stop everything right now and start using Claveman. OK, so another thing that you're starting to see on the internet, in journals, is some very cool analyses of GDELT. A guy named John Beeler, who's, I think, a grad student at UPenn, put together this visualization. This is actually a screenshot of Foreign Policy magazine. They picked it up and did a story on it. And it's a time-lapsed animation of every protest on the planet since 1979. And it gives you this very visual sense of how geopolitics has shifted based on protests. So I decided that I wanted to have something flashy in my presentation tonight. So I went and looked at what he had done, and I decided to try to reproduce this research. So I did reproduce this research, but protest is just one of the top 20 Cameo event codes. So the Cameo event codes are the types of events. There's 20 top-level ones. There's about 100 sub-level ones. Protest is one of the 20. I did it for all 20, and I did it on Tuesday, using GeoMesa and some of these other tools that I'm going to walk through at the moment. So I don't know if it's evident, but they are actually shifting, and it's showing time lapse. The point of this is that, one, I did this all on Tuesday, so I'm a terrible procrastinator, and I actually waited until Tuesday to prepare for this presentation. But two is that it doesn't matter so much because I have such robust open source geospatial tools to bring to bear that I could get it done in time. So let me jump back to the presentation and go back to full screen. OK, so I did some summary stats of this data set. On the left here, you're seeing the proportion of the different types of events over the entire time period. And one thing that I found kind of curious here was that the intent to cooperate has a slight upward trend, but actually engaging in diplomatic cooperation has a slight downward trend. And anyway, I stopped there. That's the volume of data over time. There's obviously much more data recently. That's not very surprising. So how did I do this analysis on Tuesday? Well, I started with all of the data in GeoMesa. I ingested it, so that means it's in Accumulo, and it is served by these iterators and these stacks of queries, query filtering and whatnot. Pulled the data out of GeoMesa using CQL filters for each different type of event, and I pushed the data into Scalding and Spark. Scalding is it's an abstraction out of Twitter over the MapReduce API, and it makes it very easy to express geospatial computations when used in conjunction with GeoMesa that turn into pipelines of MapReduce jobs. Spark is very similar. It's a very low latency parallel computing framework. It presents a very similar abstraction to as Scalding does, but it doesn't execute on Hadoop. It executes on its own parallel framework. So Scalding and Spark did the the heavy lifting, the aggregation and analysis, and condensed this data down into something that was tractable within R. I did some visualization using our plugins in GeoServer, but within R, I used the excellent ggplot tool to generate those time-lapse animations. So the whole pipeline, the whole geospatial analytical pipeline is all open source tools, no proprietary tools at all. This is a quick example. I don't know if you can read this, but this is an example of a density. It computes a density raster against a CQL query, and it's just a dozen lines of code. It runs in parallel on MapReduce. This is basically Scalding. Simplifies MapReduce. What we've done is we've written the source and sink implementation for Scalding to connect Accumulo to the API. And we've also hooked that into GeoMesa so that developers who want to write spatial computations or parallelized spatial computations can work with a simple feature, which is the interface that Geotools provides for dealing with this kind of data. So very simple. So how does it perform? Well, naturally on our slide we're going to perform much better than the competition, but the point is this is a log scale, and we are greatly outperforming PostGIS when getting 1,000 responses. We get 1,000 responses in less than a second. PostGIS gets it in greater than 30 seconds. There's many reasons for this. This is a little bit of an unfair comparison because PostGIS is a standalone database, and GeoMesa and Accumulo is a distributed database. But the point is that we wanted to show why you would go from a traditional architecture to a cloud architecture, what kind of advantages you would get, and what kind of problems could be made tractable when making that migration. The other thing I'll mention for the database nerds out there is that we gave PostGIS every possible advantage. We gave it tons of memory. We put the index on a separate disk partition to reduce disk seek contention. We put the index in a Linux RAM disk, so it would always be cached in memory. We tried really hard to get PostGIS to scale, and it just wouldn't scale in this particular context. And I'd also like to say that we love PostGIS. We use it all the time. So we wanted it to scale, but it didn't. OK, so where are we taking GeoMesa? Like I said, we're an incubating project within Location Tech. We're pretty excited about that. We're working on a 1.0 release so that it becomes a full-fledged project. Before we do that, there's a couple of things that I think are pretty critical. We have to have a very deep integration with cell-level security to the point that credentials and auth is passed through GeoServer so that OGC clients can reap the benefits of this kind of security. We would like to enhance the query optimization and the index optimization. We ship right now with a default index that's pretty good, but we understand the index very well, and we can tune it for other people's data. We would like to make this process automatic, so something like a vacuum analyze for PostGIS that does statistical analysis of query patterns and the data and then optimizes. We were speaking with some folks about the various advantages of all the different space filling curves that are out there, and we think it would be really cool if we could have a pluggable space filling curve that was able to adapt to the different data needs that you might have, or the different types of queries that you might have that might need location nearness in the data. GeoWebCache and Hadoop, we want to hook those two together because we visualize a lot of data, and the data that we visualize is vector data, but it's rasterized by a WMS process. So what we would like to do is lazily evaluate all of those tiles and store them in GeoMesa, so that, you know, if you made a request to see all the protest events in London, it would start to cache all of the protest events around England at various different levels of resolution and make the interaction with that data set more dynamic. As part of, you know, location tech and as part of this open source, it's very important to us that we ease developer on-ramping. Accumulo itself is kind of a complicated beast and requires some hand-holding, and so we would like to simplify that as much as possible and get people off the ground so that we can grow a community that's going to contribute back. That's pretty much all I've got. I'd like to make some acknowledgements. You know, we're really happy to be part of location tech at this point. We have been silent consumers of open source geospatial libraries for years now, and we're finally given something back, which is very nice. So thank you, and I'll take any questions, although I don't think I have time.